In this video, I'd like to go over measuring mass moments of inertia and understanding inertia ratios when dealing with any rotating application. So let's just take it for an example. We're rotating a round disc. That disc has a diameter of 18 inches and weighs a pound. Pretty lightweight, fairly small, and in theory, rotating this disc would require no torque, since forces are equal and opposite. The tangential forces that would apply torque to that disc would be canceling each other out because they're even, equal, and opposite. So assuming that a motor is mounted directly in the center of that load, the mass moment inertia for the disc is calculated with 1/2 mr squared, or 1/2 times 1 pound times 9 inches squared, which would result in 40.5 pound-inches squared. Let's go to a unit converter here. 40.5 would result in 1.678. Anaheim Automation lists motors' rotor inertias under the units of ounce-inch second squared. So 40.5 pound-inch squared is 1.678 ounce-inch second squared. To overcome inertial loads, brushless DC and servo motors require that load inertia be no greater than 30:1 with respect to the motor's rotor inertia, while stepper motors require the inertia ratio to be no greater than 10:1. Exceeding these ratios or inertia mismatches would result in the motor being unable to accelerate the load and would stall. This would mean that to rotate a disc, we would need a stepper motor that has a rotor inertia of at least 0.1678 ounce-inches second squared, or a BLDC or servo motor that has a rotor inertia of at least 0.0559 ounce-inches second squared. If we take a look at some of the smaller motors, the 08Y motor here has anywhere from 2.8 times 10 to the minus fifth up to 6.1 times 10 to the minus fifth ounce-inch second squared. And looking at our largest stepper motors, the 42Ys, they have anywhere from 0.071 ounce-inch second squared up to 0.229 ounce-inch second squared. So in theory, we could direct drive that 18-inch 1-pound disc with a 42Y 312 motor because the rotor inertia is within 10:1, 10:1 being 0.1678. But that would mean that we couldn't use the 42Y 212 because the rotor inertia is too low. So it would result in a mismatch of about 10.9, almost 11:1. This would be the case for the stepper as any direct drive, but let's say we leverage the mechanical advantage to reduce the mismatch. And the most common mechanical advantage that we could use in our stepper motors would be the gearboxes. So say take this 60mm gearbox with Anaheim Automation NEMA 23 mounting. If we use these gearboxes, the disc being pretty small, the motor, this 42Y motor here is 26 pounds. Using a 26-pound motor that would require, on these torque curves, 120 volts AC, maybe 48 volts DC, but typically the drives here, especially for a 312, requiring so much current would be an AC system. It wouldn't make much sense. So if we take a look at something mid-range with the 23 size motors, the NEMA 23s would be a much more appropriate size. In particular, let's take a look at the 23Y 206S-LW8. This one right here has a 0.0068 ounce-inch second squared rotor inertia, and it weighs about 2.2 pounds. The mismatch with that 0.0068 ounce-inch second squared to the load being 1.678 is right about 250:1. When a gear ratio is added, the advantage to the system is the gear ratio squared, so the N2 over N1, and that would be multiplied to the rotor inertia. That is, if we use a 3:1 gearbox, we would get 9 times the rotor inertia as an advantage, and if we use a 10:1, we'd get 100 times the rotor inertia as an advantage. So if we simply take the square root of the current mismatch with this 0.068, it's about 250. And we can round to a ratio to get nearly 1:1, which is ideal. But a higher gear ratio would slow down the motor, cap the speed at which you'd be able to return the disc. We can also set up an equation so we can target a gear ratio that provides exactly a 10:1 mismatch. So that would be 1.678 divided by 10. That would mean that the square root of 0.1678 divided by 0.0068 would be the minimum gear ratio, and that's about 4.97:1. That being said, anything between 5:1, because greater than that 4.97, and 15:1, which is about 250 or 225, but it'd be just fine, it would be sufficient to land that mismatch anywhere between 10:1 and 1:1 respectively. really simply, we can take a look at the cost comparison. The 23Y206S-LW8, it's 2.2 pounds, it's $103. We have 219 of them in stock. If we take a look at the gearbox we were taking a look at, the GBPH 0601 NS dash 010, that's the 10-to-1 AA231250, that's $239. We have 32 of those in stock. Or we take a look at just this motor outright, and that's 26 pounds, 771 of them. So a total for the NEMA 23 solution with the gearbox is $340 versus $770 for the NEMA 42. Also, the NEMA 23s would have a broader use for different drivers. You can select different voltages that you're using. 24 volts would work just fine. 48 volts, if you wanted to use 120, you can. But the NEMA 42s, almost strictly, you're going to be using something that's about $375. The MLA 10641. This driver right here. If I can pull that up, and this one's $375, and it's going to be just about the only one that could operate that. Or we can use the 05641s if you had 220 volt. So in theory, a smaller motor like the NEMA 17, NEMA 11, or even the NEMA 8s would be able to overcome that inertial mismatch with a large enough gear ratio, but the resultant speed would just be reduced if you use a larger gear ratio. So in theory, you could use something like a 700-to-1 gear ratio with something small, but you wouldn't have really any speed on that disc that you were running. If speed's no concern, smaller motors may very well be a good solution, but it's typical that smaller motors are more expensive than some of the standard sizes. Those standard sizes being like NEMA 17, NEMA 23, they're more easily manufactured than these NEMA 8s, NEMA 11s, and they're less material than the NEMA 42s, surely, but it's more precision manufacturing. And I will note that if you're using something like a NEMA 17 versus a NEMA 23, that the gearboxes for a NEMA 17 motor is more expensive than the gearboxes for a NEMA 23 or a 60 millimeter frame size. The costs increase fairly linearly with material costs after NEMA 23, but they increase with manufacturing costs below NEMA 17. So let's say now you have that same disc, that same 18-inch 1-pound disc, and it needs to spin at 250 RPM. So if we use the stepper motor, we might be in some trouble using that 10-to-1 gearbox. Steppers are really, really good at point-to-point positioning, but at high speeds, the torque delivery drops off exponentially. We can sort of see that here on the torque curves. As it increases in speed, there's a knee in the curve, and it goes down non-linearly as we increase speed. So we would probably need to be around 40, 41 RPS to get at 250 RPM using a 10-to-1 gear ratio. If we wanted to use something, and point-to-point positioning is no concern, and you really only care about the speed being about 250 RPM, we should be able to just use a brushless motor instead of a stepper motor. Brushless motors are much better at speed control than they are positioning control, and if you need positioning and speed control, then I would suggest going servo. But let's say that we already have this stepper motor and this gearbox, and we realize we need to go 250 RPM and maintain that speed, and positioning is not much of a concern. So using the same gearbox, what we can do is go take a look at our brushless DC motors, and the same frame size as the 23Y series motors is the BLWS 23. This is the same output shaft, same pilot, same shaft size. So that gearbox is going to mount just as well to this motor as it would to that stepper motor. But knowing that we have a 10-to-1 gearbox, we take a look at these BLDCs and understand that brushless DCs can operate at a 30-to-1 mismatch. So that means that we need a motor that has 1.678 divided by 30 divided by 100, because we have a 10-to-1, so we get a 10-to-1 gear ratio. So the inertia of the motor shaft needs to be 5.6 times 10 to the minus fourth. That would mean that these BLWS 231s are ruled out. They're too small. It would be just over 30 to use something like this. However, a BLWS 232, you'll notice that the stack length changes. Right here, it's 2.11 inches in length versus 1.72, so these ones are longer, and the motors get longer as we move on. Right, this one's a bit longer because it has an encoder on it, but these stack lengths will change, and the rotor inertia will change with them. So everybody in this series here has all the same rotor inertias. These series here is the same rotor inertias. So we understand that we can't use anything that's a BLWS 231. We have to use something that's 232. We can use 233, 34, or 35, any one of those. Next, we need to make sure that the rated speed is all okay. So since brushless motors on our drivers could operate at 10% of the rated speeds are going to be listed right here. So this whole column, anything that's within 2,500 and 25,000, because we have that gear ratio, is going to work. If you have anything under 2,500, like this 2,000 RPM motor here, or this 255 RPM, or this 1350 RPM, we can't use those because we have a 10-to-1 gear ratio. That means that we're going to get 135 here, or 25 RPM here, 200 RPM here, so we can't hit 250. It's going to be on the rated speeds. But we can use a 4,000 RPM motor. We could use any of the 3,000 RPMs, and even if we wanted to use the 12,000 RPMs, we could do that. It wouldn't be as efficient, but we could do something like that. It's typically going to come down to stock status and available voltage. So that's the next step, is what kind of voltage do we want to use. We could use 12 volts, 24, 36, 48. Even we have some that are 19 volts if you sort here by voltage. We have some that are 19, 47, 45 volts, 160 if you want to go off wall power. That would work as well. But for the sake of argument, let's just say that we select the BLWS 232 S 36 volt 4000, or we use 232D 36 volt 4000 right here. So there's 106 of these in stock. They're $76. We could use an MDC 151 050301, the brushless DC driver right here. We use the 050101. $109, 56 of those in stock. And we could swap out from that stepper motor into this brushless motor for speed. Now, if we're doing something where we have to swap into speed and positioning control, that would be in the realm of servo. That gearbox is not going to fit onto servos because these gearboxes have a NEMA mount. So you can see down here in the dimension specifications, the AA231250 would fit for the 23Ys or the BLWSs. These other mounts are typically the same, but they only mount onto the servos. So the BLK brushless motors, not the BLWS motors, or the Kinko servos, or some of the EMJ servos that we still have. So we take a look over here into the servo systems, look at the PKS FD series, and we'd be right around the 60mm frame size. So right here, these ones we want to be dealing with, whether you work on 48 volts or 120 volts, we could go ahead and go into this package here. So that would be a 60mm frame size servo motor, 3,000 RPM. We would have to change out the gearbox at that point, but there's the inertia ratio of 0.0053. Knowing that we have 1.678 and we want to operate within 30, that would mean that we need something of 0.0559. So we need at least 10 times. So anything that's greater than 3 to 1 is going to get us the correct gear ratio for at least this servo motor. So you would need a gearbox on this one, and it would need to be at least 4 to 1, 5 to 1 probably preferred, and anything closer that would get you to a 1 to 1 gear ratio is even better. But again, you have to concern yourself with maintaining a certain speed.